Hello, everyone. So this mini lecture is going to explore the ideas of temperature variation. So we've been working with the energy budget. We have seen how temperatures vary. We've experienced it ourselves, especially here in San Francisco, or I should say the lack of variation. And it turns out there's actually a reason for that. So I want to take this day to explore these ideas, and then while you're watching this, respond to the reflection questions that are on iLearn. And then after that, there's kind of what I'm considering a mini lab, where you'll actually look at the various temperature ranges for locations around the world, kind of chosen because of their various properties. So with that, let's go ahead and get into it. Okay, so let me just go ahead and full screen this here, but I think I have to swap displays. Yes, there we go. Okay, so we have 5 main methods of temperature variation. One that we've kind of talked about already with the tilt of the Earth, right? We've talked about this idea where there's a surplus of energy at the equator and a deficit at the poles, simply because of sun angle, basically. And that's because we're tilted, yeah. And then the second idea is the diurnal cycle. If you're like, what in tarnation does diurnal even mean? Have no fear, I'll go into it. And then the third method is clouds. And the fourth is oceans, or proximity to oceans and large bodies of water. And lastly, altitude. So, with seasons and latitude, try to move my camera here. So we have seasonal variations, right? So contrary to popular belief, seasons are actually not due to how close we are to the sun. And we can see that in this bottom right figure here. So it turns out actually that the Earth is closest to the sun in our winter time, right? So that makes sense. Like, okay, our winter time is generally our coolest time of the year for the Northern Hemisphere. And we're even experiencing that when we're closest to the sun. So it's all about the angle, the sun angle, and how it reaches the Earth. So really, generally, the further you are from the equator, the wider the sun angle. So it's not as harsh, essentially. So our equator regions tend to be a bit warmer than our polar regions on average. And then next up, and we can actually also see that kind of in this bottom left figure here too. So the closer you are to the equator, which is what this little person is trying to emulate, the sun is really high in the sky and the solar energy is more concentrated. Whereas in the wintertime, the sun is at a lower angle of the horizon, so the beams are way more spread out. So you're just not getting as much energy at the surface. Then, speaking of the sun, and still considering the sun as a thing, we have, of course, our diurnal cycle. So this is simply the idea that the sun is not up for 24 hours a day, for the most part, at least in our neck of the woods, right? We tend to have a day and night cycle. So during the day, the temperature increases throughout the day, and then once the sun goes down, the temperature tends to decrease, and that's what we're looking at here in this graph. So this is showing 4 separate days in February of 2014 on our x-axis, and temperature is on our y-axis here, and height is on the other side. Oh wait, sorry, no, just kidding. That's a separate one. Sorry. So temperature on our y-axis. And this is something that you can experience on the daily, right? It tends to be warmest during the day and coolest at night. It's a pretty well-known rule of thumb, and if you don't know this, you'll soon learn it. Especially for San Francisco, the moment that sun goes down, that chill comes out to play with fervor, which is pretty crazy. So then the figure here on the right is looking at, the one in the center, I guess, is looking at daytime, and the one on the right, fully on the right, is nighttime. and temperature is on our x-axis and height is on our y-axis. So we can see during the day, we have this process of conduction. So the sun is heating the very surface of the earth. And so the surface itself tends to warm up. And then convection can move that heat upwards. We talked about mechanisms of heat transfer last week, I think, or 2 weeks ago. But then at night, we have something called radiative cooling. So the surface of the earth cools down relatively quickly, and that release of heat, the heat rises, and we see, instead of a temperature decreasing with height, we see the opposite, where the temperature is actually increasing with height. And the temperature inversion is actually super, super important because it keeps things super stable and down. Or super stable and close to the surface, or depending on where the inversion is, close to, that is, it inhibits any sort of mixing. And then we have the role of clouds. So during the daytime, the clouds reflect more light. They reflect more incoming solar radiation, so then less is absorbed near the surface. So then our maximum daytime temperatures are generally not as high, and the days can be cooler. Whereas at night, the opposite tends to be true, where the clouds kind of act as a nice little blanket, and the minimum nighttime temperatures are not nearly as low, so the nights can be a bit warmer. So there's the earth is always emitting energy, but then at night, the clouds kind of act as a little layer to keep things a little bit warmer at the surface than they would be on a cloud-free evening. So those are some of the modulations. Well, diurnal and roll of clouds can be kind of like a day-to-day or almost an hour-to-hour variation. Whereas these next couple of ideas are more so on the long-term average. So our planet is made with water, right? A lot of it is water, so about 71-ish% water. So it turns out that water, being the dominant feature, it's a very, very unique molecule. And water has a magnificently high heat capacity, especially in comparison to soil. So it takes a long time for water to heat up as opposed to land. Also, soil does not mix downward. It doesn't really move on its own, right? Unless there's like an earthquake or you're jumping on some sand, but it does not mix downward on its own. But water is very, very malleable and very mobile. So it can encourage a lot of mixing going on. Also, solar radiation penetrates pretty deep into the water because it's transparent to visible light, right? So if you were at the bottom of the deep end of the pool and you had some goggles on and you lay down at the bottom of the pool and you look up, you'd be able to see all the way up, right? You'd be able to see the light coming through. But if you were in 8 feet worth of soil, you would not be able to see through that, right? A very morbid analogy would be to consider being buried alive and being buried with land versus being buried with water, and just being able to see through that in like a glass box. But if that analogy works, go for it. Or you can simply think of the idea of being in a pool. Lastly, part of the energy that is used or that makes it to the surface, the water's surface, part of that energy is used to evaporate the water rather than to heat the water. And this produces something called latent heat. And we will dive further into the idea of latent heat later on. So here's just a visual representation of the previous slide, right? So the heat capacity is way less than that of water. Heat can be mixed downward by motion of the ocean. Solar radiation makes it through the deeper layer of the water, and then part of that energy is used to evaporate. So another really good analogy for this, and way less morbid, is comparing like a piece of toast and coffee. So say you wake up this morning or tomorrow morning and you're like, I really want a piece of toast and some coffee. So think about the amount of time that it takes to heat your piece of toast and to make your coffee. And then additionally, let at least maybe part of the toast sit there for a little while and consider how much more quickly your toast cools down than your coffee or tea. So you could think of the land part of it as being the toast and the oceans as being your coffee or tea. And if we were to compare regions along the same line of latitude, so the equidistant from the equator, same sun angle, for example, San Diego versus Dallas, Texas, San Diego's average temperature range is quite minimal, right? So San Diego is this blue line here, and Dallas is this red line. So we can see that Dallas gets much warmer in the summertime and much cooler in the winter, where San Diego stays relatively moderate. And that's simply because of that sweet, sweet ocean that is basically nature's air conditioner, which is kind of cool. And we can see that with another location as well. So this is considering St. Louis, Missouri, which is near the center of the United States, versus Ponta Delgada in the Azores Islands. And you can see once again that in the summertime, St. Louis gets much, much warmer it gets much, much warmer, and it also gets much cooler in the winter, whereas Ponta Delgada stays relatively moderate. And you may be asking yourself, well, hey, what about, the temperature of the ocean? Does that have any impact? And it turns out, yes, it does actually have quite an impact. There's supposed to be plays a role here. I'm not sure why the role part is not there, but sorry. So we can see on our coastline, California has a cold current running down, whereas on the East Coast, there's the Gulf Stream, which is quite warm. And if we were to look at temperature ranges for two different locations, one on the West Coast, one on the East Coast, we can see that that is also a modulation, right? So San Francisco, again, we stay our range is pretty low, but Richmond, Virginia, which is closer to the East Coast, or closer to the coastline, closer to the Gulf Coast, has a much higher range in temperature variation. And that's, again, simply because of the type of ocean current that is right there. And then the last little bit of modulation of temperature is, of course, altitude. So in this particular figure, we're looking at two locations in Bolivia. So one is Concepcion, Bolivia, and the other is La Paz, Bolivia. And the biggest thing to point out is the fact that the elevations are so different. So Concepcion is at about 490 meters, or 1,600 feet, and La Paz is at about 4,000 meters, just above, and about 13,000 feet. So the red line is Concepcion and the blue line is La Paz. So you can see visually, even though they're close-ish to the equator, so there's not a huge range, right? But La Paz is on average cooler because it's at a much, much higher elevation. So in the next video you're going to watch, I will introduce this temperature mini lab, and you'll get to kind of play around with some of this data yourself and not just take my word for it. All right. Thanks so much for listening, and we'll see you later.